All right, so before the recap, as usual, let's take a look at some reminder. Your programming test number 1 guide has been released. I'll talk about it after the recap. Okay, I'll speak about it. And also there's a mock-up test, which I also speak about. It has scheduled on the coming Thursday in 3 days, basically, during your scheduled lab session. The mock-up test will be completely optional. If those of you who might find it helpful to really take the test like a lab test environment, feel free to come. Otherwise, the test question will be released, and also solution will be released after the mock-up test anyway. But if you want to come and try it for the first time, you can take advantage. Well, I'll leave the choice to you. And your lab number 1 solution has been released, and just remember we have gone over all the important aspects, but you're also responsible for going over the rest of the solution, right? Just make sure you get ready. And lab number 2, it's due this coming Thursday, right? Just remember. And office hour, TA contact, just the same as before. Any question in general? All right, if you've got any doubts about programming test 1, just bear with me. I'll do a quick recap from last time, and they'll dive into programming test 1. I want to make sure everybody is kind of comfortable about what's going to happen, right? So you can get prepared. Okay, that's going to be the first assessment for the semester. Okay. All right, quick recap about what we said last Thursday. It was still like a second part of the Lab 1 solution walkthrough. Let's see what you should really watch out for. All right. So the first one here is really about how we can identify, well, basically, again, we go back to the same issue about whether the multiple updates in your algorithm should be treated or should be executed atomically. If you do not think it's necessary for them to be executed atomically, then you can feel free to put multiple labels. So the PC counter is actually going to distinguish between them in different states. And in our particular context for bridge controller, this will not be acceptable because these 2 updates are supposed to be done atomically so that the corresponding invariant number 4 will be maintained, right? So just remember that, right? And also we spoke about how you can look at the state graph and try to identify that the resulting state graph over here does show non-atomic updates between these 2 variables. We spoke about them in detail, right? So you definitely want to make sure you kind of go over the recording and then also generate a state graph and look at them, right? Just make sure you're convinced. It's definitely something we'll expect you to know pretty well. Right? The second case is when we got multiple updates over here, but we get a single label over here. That one's going to guarantee these 2 will be executed in the same states. So that means when you go from the pre-state to the post-states, it's guaranteed the updates is going to do both of them. So once you get to the post-states, you will be able to still check the invariance. So for our case, you want to stick to just 1 label for a bridge controller. But I'm not saying that you should always have only a single label. It depends, right? You got to judge, right? And some exercise for you guys, if you want to check your answer, it should be rather straightforward. Feel free to drop by my office hour or make an appointment. We can talk about the issue here. Right? Again, we got 2 versions of the state graph. This will be the one without atomicity, okay? Non-atomic, how about that? And this one here will be atomic, okay? All right, and then we dive into the third aspect about the Lab 1 solution walkthrough. So this one here is really about some brush up about system variance. Also, if you look at the lecture site, let me just bring to your attention. I did mention that in the last announcement, but I want to remind you once more. If you look at the course website, and then you will see that the background study about system variant. You can click on the link, and that one already shows to you, already bring you to the particular timestamp. That one basically talks about just the pages you need to really brush up the system variance, right? You should really understand about the basics for the variance. That's something in the prerequisite we definitely expect you to know, right? So just brush it up before any upcoming assessment. All right, we talk about the notion about life lock and also diverging. You can also review it. And then we talk about if you actually got divergence, then it simply corresponds to BC loop, something like behavior in the abstract model, right? So you can also review it. That's about that's why we're reading the system variant to kind of measure your system to see if life lock can actually happen. If it does happen, we want to fix your model accordingly. Right? And we try to review the difference between invariants and also variant. Right? We can look at them and understand the details. And this page over here, of course, is just about once you fix your variant for this course here, you will not be required to come up with the appropriate variance. Instead, you will just be given some variant expression. Okay, you'll be given. And then let's say for this one here, it's 2 times A plus B, right? We'll simply try some event trace over here and try to see what's the post states in every intermediate stage over here. And we'll see that the variant value might just strictly increasing if we talk about the O events, or the variant value might just stay the same if that's also for the O event. So either strictly increasing or simply stay the same. On the other hand, if you talk about the new events, then it should be strictly decreasing the other fashion, right? So that's kind of the property we want to understand conceptually. And also for this course, you guys will have to know how to encode such check in TLA+, which we also went through in detail last time. Okay? That's about the variance. And this one here, just to remind you that we did have some proof obligation in 3342. Of course, you don't need to do proofs anymore for this course, but it's also kind of useful, right, for you to brush up the concept about variance. But guys, any question about system variance you want me to clarify in class? If no, I'm going to assume you're going to look at the background material to recall the details. All right? Okay, I see most of you agree, so that's good. All right, so this one here, the last thing that we spoke about last time is to take, basically you can see this is the M1 variance. We basically took the M1 no variant version and try to extend it with several variables and also several checks and also several updates in the model to show you that exactly what you should really introduce to really check the system variance. If you're ever tested about this kind of concept over here in the test, it could be a written test, it could be a programming test, or even in the exam. You will always be informed about which events should be the old events and which events should be the new events. You will be told directly, right? You don't need to somehow figure out, because we don't really dive deep into refinement for this course. So that's something you can assume. It will always be given to you. Right, so we talk about this conceptual sketch over here whenever you want to go from the pre-state to the post-state. So there are 2 cases about event transition, which can be either by the old events or new events. And the corresponding relationship will be different, right? So that's also something you want to understand and also know how to do them, right? And we talk about in order to check the system variance, you need the pre-state version for the variance. Also, you need the post-state version for the variant, right? So these 2 are going to be placed before and after the action of the event takes place, right? Conceptually. And you're going to look at exactly where they're placed. And also, we got these 2 flags over here just to tell us the event transition that just happened. Should it be an old event or should it be a new event? Of course, these 2 Boolean flags cannot be true at the same time. It's got to be either both false in the beginning, no event has happened, or at least one of them, exactly one of them should be true. For example, this one being true and this one being false tells me that the event that just occurred is an old event, which I can expect the variant value to change accordingly, right? Etc. Right, so you guys can look at the different annotation I made over here. I may not repeat, right? To save some time, you can look at and let me know if you got any trouble understanding. And these 4 conditions over here are the final ones we're going to check about the variance, right? Especially for this one here. So this is really to say we're using implication. Depending on whether the last transition is either an old event transition or new event transition, we're going to check the variant value differently, right? Depending on which one we're talking about, right? It's also very important for you to understand. Here, we're just using a very useful application of the logical operator over here, implication. John?
How come in the first one we didn't say like in NAND, we said greater than or equal to 0?
Yeah, it's the same. So here, when you say this, if you say this is a member of natural number, and we know that for our course, right, it's a larger than or equal to 0. They're equivalent. So you can feel free to maybe replace this one here to say in whatever keyword it is for natural number. That will be fine too. Okay, you can feel free to use either one. Right? Of course, if I put either one over here, you would know which one should be, they are actually both equivalent. On the other hand, if I say it's a member of, for example, integer, then that will be wrong, because variant cannot be negative. So when you say it's a member of integer, it's too weak. All right? Things like that. All right, that's about a recap from last time. Guys, any question before we dive into programming tests? Yes, go ahead.
Sorry, Professor, are those four conditions always fixed for all variants?
I would say, okay, so the question was, are these the kind of the fixed pattern here for checking variance? The short answer is yes. So for example here, so this part here might be different, right? Depending on what the variant expression is. This one might change. And for this part here, like what I answered to John, you can either say larger than or equal to 0, or you might say it's a member of natural number. Okay, so this one pretty much the same each time. And this one here will also be the same because we are always using these two flags to see what the last transition was. That will be also the same, yes. And these two, I think so, also the same, yes. They are pretty general pattern to really encode, okay. And I think one of you actually asked me, back on Thursday, around Stedman Lecture Hall, maybe after class, you were kind of asking, so is it possible to somehow factor out certain update to make it a separate label, right? That one has to do with the atomicity that we spoke about. So I would encourage you guys to try maybe different variants. Well, maybe I shouldn't use variant, that might confuse you. Maybe different changes you can introduce to the model over here. For example, let's say, just very quick, right? There's something you can definitely try. I'll show you to you. You can see here we got vpost appearing once over here. We got vpost appearing the second time, vpost appearing the third time, and vpost appearing the fourth time. Right? You can see the same line updating the post value for variance is repeated 4 times. Is it possible, when you were coding, you always know that you should really have minimum number of duplicates. Is it possible to say, I'm gonna factor this common line over here into somewhere later and make it a label separately? All right, that's something I would encourage you guys to try. If you try it, if it works, that means it's okay. If it doesn't work, if you got any failure about the variant checks, that means it doesn't work. But what's more important is, if it doesn't work, you got to dive into the error trace to see why it doesn't work. My hints for you would be, think about atomicity. All right, think about it. That's some exercise for you to try. I think that'll be also useful to further advance your understanding. All right. All right, any more questions about what we covered last time? All right, so now we draw a closure on lab number 1. So you guys going to look at the solution and let me know if you got any other concern, okay? And of course, lab number 1 will be covered for your programming test 1. I will talk about programming test 1 right away. All right, let's now talk about programming test 1 right here. All right, if I show you the semester calendar over here, right, just now let's be reminded about where we are in the semester, okay? So we are now here today on week number 5. We're now lecture 9. We're right here, okay? So this coming Thursday, optional attendance if you want to take the mock-up test. We're going to start 9 a.m. in time, just like the real test. It's going to be set for a timer for 15 minutes because the rule is we got to leave 10 minutes to actually before if there's any other like a lab going on. But just officially, we have to end in 50 minutes. I kind of push that as much as possible for the regular time. All right, so I'll send you a reminder. And then next Thursday on the 13th, it will be the actual thing, programming test 1, right? The procedure and the process will be very similar, except that in the actual test, we're going to take attendance, of course, right? We're going to send you out. For this coming Thursday, you don't need to sign up, right? So you can also practice submitting stuff at the end as well. Okay. All right, so that's about the calendar you can remind yourself about. And then if you look at, let me see anything else. To really find the guide, you can see that's on the lecture site, right? You can click on that, and then I'm going to go over that in detail, okay? Because that's your first test. I think for the second test, it will be very similar, so we don't need to dive into so many details. But for the first one, let's make sure everybody is comfortable. All right, so let's now look at the guide, right? There we go. Okay. All right, it's going to be Lassam Building 1006 next Thursday. Okay, and then I think everybody will be there. Tentatively, there'll be no seating plan. You can just sit wherever you like. But we'll see. There might be certain area that we want to just keep empty, but I'll let you guys know. But for now, there's no seating plan. And the lab here, and then duration will be 50 minutes, and it'll be from 9 a.m. to 9:50 a.m. I know it's early for some of you who have to do some long commute, so please plan your trip or plan your time accordingly, right? It has to start in time. All right, it's going to be in person, all right, and then 10% of your course grade, just according to the syllabus. Primarily a programming test, meaning that, so there will be 2 tasks, which I'm going to talk about. And one of them, I also need to dive into detail to give you more conceptual clarification. So the programming part definitely will be more about writing algorithm in Pascal and also write the complete post condition. That's something I'll speak a little bit more about. There might be other tasks where I might just say, now, given this particular module, TLA, that's partially completed, I may just ask you to load it or import it into TLA Plus and maybe answer some question. Remember in Lab 1 tutorial video, whenever you want to write something like an answer to written question, you can write it at the bottom there as a comment, right? That's really where the question can be. So, but I will definitely consider you got 50 minutes, so I'll try to balance out, okay? But you got to get prepared for both possibilities. You got to be very clear about what the Pascal syntax should be, given that you're completing 2 labs, and then both the algorithm and also assertions. There should be no syntax, no type, and no logical errors to receive full credits. And then also, if I can ask you to load the module and then answer some short, maybe to put the answer for some short answer question, right? You got to make sure your answer really right to the point, because TA are going to grade manually. Right? So these are the 2 possibilities, right? And there will be documents there that's given to you during the test to really look up the syntax, right? I already mentioned that in Lab 1 and Lab 2. So that document will just be there, right? If there's anything you think that might be useful for your development for Pascal algorithm, but it's not in the guide, you should know them, right? There's no data sheets allowed in the actual test, okay? All right, so you will be required to use a TLA toolbox, that's obvious. And then, so there are 2 possible tasks during the programming test, okay? The first one will be the primary one, okay? That one there, you're going to know how to create some modules from scratch, pretty much like a lab number 2, all right? You're going to create a module from scratch, and then for each module, you're going to implement some algorithm, and we will give you some input and output description about the required input variables, output variables, and what should be the relationship between them. It will be clear. And guys, this is very important, right? Because somehow we're going to run some automated tests as well on your algorithm and also assertion. Whatever names that are suggested in the instruction, you got to follow them faithfully. Of course, you wouldn't be given 0 if you didn't follow the name. The TA will maybe try to fix them for you. Hopefully, they'll be easy fix, but there will be some penalty. All right, so please make sure you really follow the exact names. I'll be very explicit in that instruction. You will see that also on Thursday when you take the mock-up test. All right, so just notice for this one here. And then the assertion, okay, so I'll talk about what I really meant by specify, complete, precondition, and postcondition. I will clarify that, right? That's more also like a mini lecture to make sure everybody understands, okay? And also, you got to know how to auto-translate the Pascal algorithm into TLA Plus if you want to check something, right? For example, if you want to check the invariance. All right, and then, okay, this is very important, okay? Because most likely the algorithm you're going to implement will be more like, maybe not the rock, paper, scissors, which does not have to involve a loop. But let's say if you remember the suffixes problem for your lab number 2, for that one, you definitely need a loop. You got to be very careful. Because the way they're going to build a reachability graph is by running your algorithm and see how far the states can reach. If you got some infinite loop, that means the process of building the reachability graph is going to hang there without ever terminating. So during the test, it will be completely your responsibility to make sure you write your loop very carefully. Try to avoid infinite loop. Hopefully that's something you kind of experience when you're completing the lab before the test, so you pretty much know what you should do. If there's some infinite loop that your code doesn't really terminate, when you try to check, then of course you're going to waste some time, killing the process, or in the worst case, you may even have to restart the lab machine, right? So we are not able to make up the time for you. So you got to make sure, be very, very careful about this warning here. That's from the experience of your fellow students 2 years ago, All right, so just watch out for that. All right, so that's about the first task. And as I said, I'll speak more about what I really meant by complete postcondition. I'll get there in just one moment. And the second possible task would be you might be asked to import some given module. The module may be already completed, but contains a bug. I may just want you to find the bug. Right? You may have to run the checks and then look at the error trace and see how to fix the model accordingly. That's what you did for lab number 1, for example. Right? Or it might be that I give you the almost completed module, but without any variant check. In that way, you may have to extend the code to make some variant encoding and checks, something like that. All right? There could be many possibilities, but just make sure you go over all the lab 1 solution and also lab 2 solution as well. So next Tuesday, because your lab is due on Thursday, so for next Tuesday, I will also go over with you the lab number 2 solution, especially the task number 2 and 3. I think they will have certain complicated postcondition that you might need to know how to write in the actual test. But of course, before the submission deadline, you should already try to figure out exactly how complicated or how complete your postcondition can be. All right, you still have time to work it out. All right, so that's the task number 2. But primarily, this will be the more weights for the test. And this one here is possible to be there, but it's going to be slightly less weight to emphasize for the test, right? If that's something you're interested in knowing. All right, and this is also important, right? So submission. So you got to make sure, I will try to remind you guys maybe every 15 to 20 minutes, and then you really want to maybe submit your intermediate work by very easily, just go to web submit link and then click on this module you want to support, you want to submit for grading, right? You want to do that periodically. In the worst case, if you don't really want to do any intermediate submission, that's your choice, but you got to make sure to leave yourself enough time to really submit at least give yourself a few minutes. If you cannot really end up submitting anything for grading, too bad, all right? Please make sure you really submit things in time, okay? It's better to understand about the requirements about this one here before the test. You really got to make sure you submit in time. Okay, this one here might also be useful. So especially for if you are supposed to implement the algorithm and postcondition, you might find it useful, let's say, if the assertion or the algorithm contains certain issues, you may want to look at the state graph and error trace side by side, right? So I will include instruction about how you can set up the state graph itself, like a way you can find the path to the dot program, and also like which system preference you have to, which project preference you have to tweak, right? That's something I will also make sure that's in the markup test on Thursday, so you can also try to practice as well. Okay, I'll make sure it's there. Okay, state graph. However, exactly how to generate that graph, given that the tool has been set up for you, how to generate the graph and how to interpret the graph, it will be up to you. We cannot really help you. That's part of the test, right? Okay. All right, submission for grading. So there will be multiple files you may have to submit for TLA. You just got to make sure after you submit, you may want to leave yourself enough time so you can download the files you submitted, make sure that's the one you want to be graded, right? So really make sure you do that periodically during the test. Okay, grading criteria. Okay, I would say about the penalty, I really hope nobody is going to receive any penalties. So these are very easy to avoid. Make sure you're familiar enough with the syntax about Pascal so you don't really have to require the TA to fix anything for you, all right? And number 2, you want to make sure the input and output variables are exactly what's in the instruction. That's also easy to avoid, this kind of mistake. Okay. And then, so to really, if the question itself requires some short answer, then the TAs are going to grade them manually, right? That one's good, right? That one, not much to say. And this is the stuff I want to talk about, all right? Okay. So we want to talk about what does it really mean? Well, what does it really mean for the correctness of your algorithm and also the correctness of your assertion, right? I got some very brief description over here. You can take a look. That's basically how we're going to grade your assertions alone. But we're going to look at some mini lecture just to understand the full picture. So you'll be very clear. You can even try to also practice that even in lab number 2. Okay. All right, the format, this document will be made available to you, and then there will be instruction about how you can set up the state graph, okay? And whatever you learn in lab number 1, you are also expected to really operate that, in the tool. Okay, that's why we gave you some detailed videos for lab number 1. Coverage, lab number 1 and lab number 2. You do not need to review the lecture material for the programming task. You do not need to, all right? So the conceptual question you might be wondering, so should I study the lecture to really get ready for maybe short answer question? You don't need to study a lecture for that. So what you need to do, the only exception will be you may want to look at the lab 1 solution walkthrough that we had last week, and also next Tuesday about lab number 2 solution walkthrough. Those are possible, those are valid coverage for the test, okay? If once we start covering about temporal logic, let's say maybe not today, maybe Thursday, also that one you don't need for programming test 1. Okay. All right, for mock-up tests, they will be 9 to 9:50 this coming Thursday, and then some practice question will be made available to you. All right, but again, guys, I cannot emphasize enough, the practice question there are not meant to be complete. That means some aspect that may not be covered by the practice question, they might still be in the test. So that's why you got to study according to the coverage, right? Just some example. And also the practice question, some of them might be at a similar level of difficulty in the actual question, but some question there in the actual test may be harder, right? So you just got to study and review everything, okay? These are mainly just for you to get used to the flow and format. That's the main purpose. Not to really give you something that will be equally difficult as the actual test, right? I want to emphasize that before the actual test. So you really want to make sure you get prepared for everything that we already covered in these 2 labs. All right. All right, so this section 5 here, I'm not going to read it. So this one is just about, for those of you, either you cannot really attend the mock-up test on Thursday, or if you want to maybe somehow simulate the test again yourself, you're welcome to do so. I just included some instruction over here for you. You can just set yourself a timer and then get it done over the remote lab. It's going to be pretty close to the actual test. You're just going to give yourself a little bit good pressure, about the time. And the actual practice question will be released after the mock-up test. So your mock-up test will be on Thursday. I will get them released by the end of Friday, the next day. Okay? You can also take a look and also release the solution as well. You can try. All right, any question about the guide for programming test 1? Yeah?
I have a question on lab 2. What's the exact syntax for the statement? I kept forgetting.
If that's specific about syntax, why don't we deal with that after class? Let's do that. Okay. Yeah. Okay. Any question? Yeah. Go ahead.
Do we know everything mentioned in the Pascal document, like the syntax document?
I would say focus more on what you will need to solve the problem for lab number 1, lab number 2. So that's pretty much what you will also need for the actual test. If there's any additional construct in the document, I think it will be also beneficial if you kind of know they exist, just in case you might need them in the actual test. So the short answer is that document is what's going to be given to you. If I were you, I will actually get myself very familiar about what's really there. Yeah. Okay. Yeah.
How many questions are we expecting?
That's something I don't have a precise answer just yet. So, but I would say, as I said, you might get questions related to maybe post-condition writing, algorithm writing. You might also get questions related to maybe some short answer as well. So exactly how many, I don't know yet. I'm still trying to look at the test and work with the TA to work out the exact question. Yeah. Mm-hmm. Yeah.
How does the automated grading work?
How's the
Automated grading?
how does it work? Okay, I'll talk about it. Yeah. When I say auto, yeah, I'll get there. It's mainly about post-condition and also the algorithm. Okay, I'll get there. All right, if no further question, let's now deal with some very big question mark from this guide over here, which is about the precondition, algorithm, and post-condition. Let's just clarify that in a general way as much as possible. Okay. There we go. All right, so I'm basically going to talk about precondition. Also, I'm going to talk about post-condition and also I'm going to talk about implementation as well, right? I'll speak about each one of them kind of in isolation, but they're kind of related to each other anyway, okay? So before we dive into some very simple, concrete example, let's just talk about in general, all right? Right, you got your module here, and then you got some algorithm, all right? So before the actual main program, which will be the algorithm that you have to implement, usually you have to set up some variables. And usually for input, it's going to be some constant. So when you actually launch the checker, you can set the input to be some specific value. For example, maybe for one test, you want to make it 1, 2, 3. For another test, you want to make it 3, 4, 5, right? The constant can be changed every time you want to create a new model for your module, right? And the input over here may be more than one. For example, you might take some input sequence and maybe some integer value, right? And the output typically just one, but it could be also two, right? I'll make it very explicit and clear in the instruction. But for now, let's just talk about we got one input and one output, okay? So the structure would be we got precondition over here. And for now, I simply, each one of them is going to be assert. So here I just put one single precondition, right? But there could be multiple. Okay, so precondition here. That's one section here. And then we also got another section here, which will be the actual coding, which will involve maybe variable assignments, if statements, and also loops, etc. That's exactly what you have in the lab number 2, right? And the ending section there, assuming that if your algorithm terminates, we're also going to check something as the post condition. So here I just put R1 and R2, just in general, just 2. But in general, it could be more than 2. Can be 3, can be 4, can be 1, can be 5. Can be some arbitrary number. All right? Just before that, let me clarify some terminology very quickly. You may have seen this maybe in 3311, the software design course. We say that the precondition and also postcondition. Okay? So the precondition over here, that section there, and also the postcondition. So these are so-called contracts for your implementation, right? So they are supposed to be not written in the imperative form like a code. They're supposed to be specified in predicates, contracts. They are more, in a way that's more abstract, like a higher level for people who don't really want to dive into the implementation detail of your code. They can only look at just a precondition and postcondition. Well, we'll see some complicated example once your lab 2 is due, right? But you should really try to figure out something before the submission deadline. All right, so these two are what we call the contracts. All right, and I'll talk more about also pre-state and post-state. That's also important. Right, you can think about here, the precondition is more about the pre-states. That's right before the algorithm starts executing. And also we got the post-condition over here. So that's assuming that the algorithm already terminates. So that would be where the post-states occurs. However, the post-condition in general does not necessarily only concern about the post-state value. It might also refer to pre-state value as well. Okay, may not be some concrete example today, but just in general. Okay, so think about the post-condition here. May involve both pre and post-state value. All right. We'll see some concrete example in a moment. Okay. Let's first of all talk about the Q. And the Q here is about the precondition. Okay. Oh, sorry. The Q here is the precondition over here. So what does it really mean when the precondition is actually complete, right? Let's just clarify that. Over here, the precondition here is like a predicates. Predicates which states the assumption on the input variables only. And the assumption is actually made by the algorithm. All right, so basically you want to check before the algorithm is actually going to start executing, we want to make sure there's certain assumption that will be made. Okay? So conceptually, think about what's going to happen. That's also what's going to happen in the evaluation as well. Okay? So think about if all the values for the input that's going to satisfy the precondition will be in this set over here. Okay? So now if you pick any member from there, so let's say some value v. V here satisfy the precondition. That tells you that the algorithm should be able to handle this value here and set the output accordingly, according to the problem description you're given. All right? That's one case. Sorry if that's a little bit blocking, but anyway, you got a recording and also you get a copy. I'll read it out when I write. V will be an input value satisfying Q. Okay, I'll put it here, running out of space. Must be map by the algorithm to the correct output value. Okay, what I'm saying here is, think about if I got this particular V here that satisfies the precondition, then I should be able to pass the V conceptually to the algorithm, and the algorithm is going to set the output variable accordingly. Right? Everything is going to satisfy input-output relation. Okay? What about value outside Q, like a value that does not satisfy Q? That will be the value the algorithm should never have to worry about. For example, if you want to do division, x divided by y, the algorithm itself for division does not need to worry about the case where y is equal to 0, because that one should be a precondition. Right? And we'll see another slightly more complicated precondition for you to think about in just one moment. So conceptually, you should also understand over here. An input value not satisfying Q is assumed not, again, let me put it here, assume not to be passed to the algorithm. Right? You got to be very clear about the boundary that's defined by the precondition itself. Right? Let's say when we grade your submitted solution from the test, right? Just about the precondition itself, we might say we pass certain input that is supposed to violate the precondition. That means we should see your submitted precondition should fail, right? Because it gives you something that's invalid. On the other hand, if we give you some valid input value, then your Q should not really fail. Right? How do we assess? So there are two possible ways. Given valid input, your Q. When I say your Q, I really meant the Q that you specified during the test and submitted for grading. Must pass. And number two, let's say given invalid. Okay, let me write a little bit better. Invalid input, your Q must fail. Let's go back to that division algorithm example, right? So your precondition should be, for example, y is not equal to 0, right? So now if I try to give you the input where y is equal to 0, in that way, your assertion for precondition must fail, right? If I give the y to be any value other than 0, then your assertion Q should not fail, right? That's how we judge. We're gonna try out different input values and to see whether your precondition is gonna fail as expected or is gonna pass as expected, depending on what the input is. Right? Hopefully that's clear to you conceptually. All right, so that's a general principle about precondition. And let's now talk about one specific example, just to give you a little bit more concrete understanding. All right, guys, this one you should know pretty well from maybe 2101, data structure course, or 2011. Okay? Let's say the algorithm is to implement a binary search. Let's say iteratively. Okay? We don't need to worry about recursion for this course, for plus count. Let's say it's a binary search, and then the input is going to be some input sequence and some input value. Let's say 2 inputs. And the output is going to be some Boolean value. Initially, let's say it's false. Let's say. What would be the precondition? Daniel. Yeah, that's pretty good. Well, I'm pretty sure everybody knows, right? So now Q over here would be, for example, the input sequence is sorted. Oh, of course, in the actual test, this is not something you should write. I'm just telling you informally what it means. And it will be exercise for you to say, given some input sequence over here, how would you express the quantification expression to express that the input sequence is sorted? All right, exercise for you. That should be rather easy. You don't even need nested quantification. All right? Exercise. Think about it. All right, so that would be a very reasonable precondition. And now, for example, let's talk about it right away, right? So now how do we, let's say you specify something. Let's say you submit something like a Q for grading, right? Q is actually some predicate. That's invalid syntax. And we might try to, for example, passing, let's say here I got 1, 2, 3, and 4. Apparently, there's a sequence that's already sorted. It should be valid for binary search. Should not trigger any precondition failure. And when I say precondition failure, that means none of the assertion representing the precondition should fail. Right? That's in a more general term. Any precondition errors. On the other hand, second case, if we give you some invalid sequence that cannot be appropriate for binary search, we might give you, for example, let's say 1, 3, 2, -2. Right? It's not exactly sorted, apparently. Right? Should trigger some precondition error. Right? So here we are basically testing for passing. Here we're testing for failing. And both, your precondition should really work for both cases, right? Of course, the actual precondition might be a little bit more complicated, or it could be easier, right? Depends. But it's important to see the concept over here. All right, so that's about the precondition. Any confusion or anything you want me to clarify further? That's about precondition. All right. And let's now talk about the middle part, which is the implementation. And then we'll talk about postcondition, which is going to be the more sophisticated one, which we're going to get into as well. All right, so now let's talk about implementation, right? The middle part. Okay. So the middle part here is we're assuming that the input value that we're working with for the algorithm already passed the precondition. We assume that, right? Otherwise, you cannot even get there. You might just have got already some assertion error before that. Right? So I'm going to write down some general comments over here, and then we'll see how we can get from there. Okay. So let's say over here, what does it really mean when we say implementation correct? So by the way, so what we are talking about over here about precondition, postcondition, implementation, correctness here, we will get a more formal, of course here you guys are doing some model checking, but we're going to see how you can also do some paper proof. It's more to do with the program verification, which we'll get to once we talk about temporal logic. That will be the last about 1/4 or maybe 1/5 of the course towards the end of the semester. So what you're learning now is also going to be useful for a later lecture. Okay. So given that the input satisfies the precondition Q. Right? So we talk about the precondition just in the previous page, right? Given that the precondition is already satisfied, we're basically asking, does the algorithm terminates in a state where the output has the expected value? That's a general term, the general expectation. And I'll give you some example. Okay? Does the algorithm, and of course, the algorithm I'm talking about over here is exactly what you specify in the programming syntax in Pascal, right? Does the algorithm terminates in a state where the output variable has the expected value? Right, like that. That's the general principle. Of course, that's obvious, right? I'm pretty sure that one you have no trouble understanding. But how do we actually check about the correctness of the algorithm? So there are two possible approaches that you can also imagine, right? So both are fine. So you can feel free to try both of them, but I'm going to lay them out, and then we can discuss about which one might be better. I can tell you the second one is going to be better using postcondition, but I'll put it here. Okay? So there are two possible ways to check for implementation correctness. So just before that, let me just make more space for myself. Just bear with me. Sorry. There we go. Okay, I'll make it a little bit smaller here, so I got more space in there. Okay, so there are two ways for asserting the actual output. So there are two ways for asserting the output. Okay. So one will be the more specific way. Okay, the specific way will be conceptually think about the algorithm itself. It's like more like a function. Okay, so you're basically saying my algorithm over here, and then let's say there's only one input for now conceptually. So I'm gonna pass some specific input value. Let's say input number 1. Okay, so the algorithm is going to return some value. So you can think about so this expression over here is about the actual output that's produced by the algorithm, given input number 1. And of course, you may change the input to be input number 1, input number 2, as many as you like. So think about this is the actual output produced by your implementation, right? So this is the actual output. And then we want to make sure that this actual output is the same as the expected output number 1. Right, let me just give you one more. Okay, and then you want to run the same algorithm, but now I want to try the different input value, maybe input number 2. Let's say the input number 1 is more like an empty sequence. Input number 2, maybe it's like something that's almost sorted, something like that, right? So you can give different input value. And this will be expected output number 2. Okay, so you can think about every time if you want to test for this particular case, let's say a test case, what would you have to do? All you do is when you create a model, of course, you're going to set the input to be certain value for the constant, right? What about expected output number 1? You can easily just say for my post condition, I can simply say assert, I can say output is exactly equal to expected output number 1 for that particular run. But you can already see what's the disadvantage for this. That means every time you want to try the different input, you have to change the corresponding expected output. right? You got to change it. You got to modify your module every time between different input. All right. So the drawback is the assert expected output number 1 or output number 2, right, has to be changed according to what input you're talking about. According to the specific input. But when you do your lab number 1, this might be the more straightforward way for you to think about specific, right? You can feel free to try. You just gotta say, I'm gonna instantiate my model and then set the input to be a particular input sequence. And then the output, I need some very specific value to check. That's one way. And the second way is more general, okay, the second way. So this is number 1, okay. For number 2, I'm running out of space. I'm gonna put it on top, okay. So number 2. Number 2 is going to be the more general approach, which we hope you guys will pick up from lab number 2, all right. The more general approach is we're gonna specify different predicates over here as post condition, right? Maybe just one, or maybe it can be more than one, right? Depends on the situation. And the general approach goes like as easy as this. The general approach will be we just specify one or more predicates assertions, right? You are going to have R1, R2 over here. And also that's something you will do for lab number 2. And also when I go over with your solution for lab number 2 next Tuesday, you also see. More predicate assertions, each one of them is going to relate the input and output variables, basically. That's a general term. Relating the input and output variables. And the good thing about this general approach is once you specify the post conditions over here, you do not need to modify this anymore. Whenever you instantiate your input to be some particular value, these two will be checked just the same. It's going to be independent of particular input values. That's the beauty about general post condition, okay? Okay, so for number 2 over here, the post condition do not need to be modified, need to be adapted for different input values. You do not need to. That's really the key. Separating between the specific and general approach. And of course, you should know both. And number 2 is going to lead you a longer way, for sure, for this course. All right, let's see some very quick example. Very quick, okay? All right, so now let's go back to our binary search example over here, right? Just binary search. Okay, so let's now talk about approach number 1, right? The specific one, right? That one's pretty easy. That one there, I just give you one, and you will see right away the idea. So approach number 1 about a general. All right, so maybe somehow we can set the input constant to be, for example, let's say 2, 4, 1, 3, right? That's the input. And then you're going to write some corresponding post condition. And then we can simply say assert at the end, right? At the end. The output is simply equal to 1, 2, 3, 4. Right? Easy. Oh, that's about sorting, right? I beg your pardon. Okay, that one is about sorting. I'll give you the actual example. That's not even binary search. I thought it was sorting. Okay, so that would be an extra example for you. So this will be just sorting. And for our particular example here, you can see you got input sequence, you got input value, right? So it could be that. So the input, let's say, again, 2413. Input sequence. And the input value over here, let's say we're looking for maybe 5. 5 is not there, right? So what you can do is you can say assert the output here to be false. Okay, so this is just another this is the actual example I meant to give. So that one's about binary search. All right, like that. And number 2. Again, I really didn't want to make this typo. This will be, of course, the specific one. Okay, that's a specific one. And the general one is going to be you have to specify something as predicate here, also for the assert, right? I'll give you guys some hints about what you may specify as a complete post condition, right? So here we got, so for example, you might say the input sequence is unchanged. Also, you might say, when I say unchanged, for example, if you're given 2413, I want to search for 5. You don't really want to modify the sequence, maybe remove some element from there. You don't want to. Right? So that's, you want to make sure the input sequence is unchanged by the searching algorithm. And the number 2 over here would be the output must be computed properly. Okay? This one here, pretty easy, so I can tell you right away what it might be like. On paper, of course, you got to work out the syntax. You might say the output over here, which is a Boolean variable, that will just be set to whether or not the input value is a member of the input sequence, right? That's what you're going to specify, right? So post condition number 1, post condition number 2, arguably, they are complete. Okay, I'll talk more about complete once I get to the third part, which is about post condition itself. So you guys, you can imagine that when we test your algorithm for correctness, we might follow either specific or general, or a mix of both. Right? Of course, when you test your algorithm, you can also try either or both of them, right? Just to be precautionary. Okay? So for general over here, you just have to specify the complete set. So again, I'm going to talk about complete a little bit more in the next page. We're still talking about just the algorithm itself, but we're going to speak about exactly what post-condition completeness really mean. Okay, that will be the third part. The complete set of post-conditions to be check. All right, that's basically what we're going to do. All right. Okay, one final part. Okay. So, question, Farrads.
About last slide.
Yeah, of course.
For the 2413, we wouldn't even go to the post condition, no? Because it's not sorted.
Absolutely. Thank you. That's a very good point, Farrads. I was just reducing it. Apparently, that's not a good idea. Thank you. Absolutely.
And another quick question. For the, when you say output is input value as a member of the input sequence,
What do I mean by that? So think about output here is going to be, you can think about this equal sign here is like if and only if. So we're saying the output value, which is either true or false, it will be true if and only if the input value we're searching for is in the actual input sequence. So here we're just trying to assert about a search result, We didn't search any specifics about how you actually implement the binary search algorithm,
Okay.
which is not.
So the value doesn't even exist, then that if and only if fail.
Yeah, exactly. So you can think about if the output is actually true, that means this one here should be there. If the output is actually false, that means this membership here must be false as well, right? That's why we say if and only if. And equal sign here is a very useful operator to use, actually. Yeah, question? You got a question or not for you? Okay, it seems like you're fine. Go ahead, Vincent.
The first post condition, why is that one necessary?
That's necessary because imagine this, which I also get into, but let me answer that right away. Let's say, for example, you guys are input sequence over here, right? You want to search for 5. Let's say the output is set to be false. However, I also remove the third element always by my algorithm. Is that supposed to be happening? Not really, right? So in some way, the binary search is more set like a query or accessor method, which is not supposed to really modify the input. So that's why this kind of post condition is very crucial. Before you do anything to assert about the actual value for the output, you want to make sure the input should stay unchanged. Okay, that's actually very important. Yeah. All right, final part. Okay, and then we'll take a short break. Final part. All right, so the final part over here is about the post condition themselves, right? So we're going to talk about what do we really mean when we say the post conditions are actually complete, right? So let's now define them, and then I'll give you example. And back to our binary search example. Okay. So here, just in general, we're not even talking about binary search. Let's say if we got R1 and R2, let's say we got 2 post conditions separately, right? Well, it could be 3, can be 4, can be just 1, right? Arbitrary number. When we say these 2 are considered as the complete set of post conditions, what do we really mean? We mean the following. That means these are complete if the kinds of implementation errors, and of course implementation errors can only come from the algorithm, right? I mean the middle part over here. Are captured by either one of them. If there's any error, that actually occur, implementation error, like a logical error, that occur in the algorithm, either R1 should fail or R2 should fail to really signal there's something wrong. So the post condition has the most value when it fails if there's the implementation itself is actually wrong logically. Okay, I'll give you an example in just one moment. All right, that's one way to understand it. Another way you can think about R1 and R2 in this case can kind of capture or address all the possible ways that your implementation can go wrong. Okay, if they, of course, when I say they, I mean R1 and R2. Okay? If they address or account for all possible ways that the implementation can go wrong. I can tell you that this interpretation kind of tells you that in general, when you are given no hints, specifying post conditions that are complete is a challenging task, right, in general. That's why we're learning it, and we try to practice that. All right. So let's now take a look at some example, and then I'll show you exactly, applying this kind of idea, how do we assess the quality of your post condition, right? That's something we'll see, okay? All right, let's now switch to our context for maybe the post condition. Let me say one more thing, okay? Let's say in the actual test, maybe we ask you to specify R1. We also asked you to specify R2, right? Say you are required to specify each one of them. And then you want to submit for grading. So what you guys asked about, how do we do auto grading? So this is where the auto grading might come from. Okay? Let's say in general, and I'll switch to a specific example. Let's say for R1 only, R1 catches certain implementation error. So what we'll do is we're going to replace your implementation here by some faulty implementation that we created. We're injecting some error into your code. And then that one there should trigger exactly the R1 you specify, right? If somehow this faulty implementation is approved, agreed by both of your post condition, then you'll be in trouble. That means your R1 was not specified properly. Okay, let me say one more time, and I'll give you a specific example. R1 and R2, each one of them is supposed to capture certain kinds of implementation error. So the way we assess whether or not you specify them correctly is by as follows. Let's say we want to test for R1. We know under what circumstances R1 should really fail as expected. So what we'll do is we'll inject the corresponding errors into the algorithm here, or just replace it by some faulty one. And that one there, when we run it, it should really fail R1 that you specify. If it does, you get the marks for that particular part. If it doesn't fail, that means there's something wrong with how you specify it. All right, so we'll try different test cases. All right, that's the conceptual idea. But let's see some concrete example to see exactly what I mean. All right, let's see that. And this might also clarify what Vincent was actually wondering about, right? I'll also show to you, okay, about why we need the first one, okay? Let's say here, let's say R1 and R2, let's say something you kind of specify according to what I suggested earlier, right? So let's say post condition number 1 is about the input sequence should be unchanged. And post condition number 2 is the output is computed correctly. So we'll give you some hints about what R1 and R2 should be specified in the actual test. So you will just formulate a condition accordingly, right? And then let's say this. Okay, let me just go back here. So let's say R1 over here, right? I'll just say unchanged, just to remind you. Unchanged input. Okay, and R2 over here is about correct output. And let's say both of them are the submitted answer by you. R1 and R2, both of them are answers submitted by you. So now, how do we auto-grade? In some ways, it's not completely automated. We still gotta, set up the input and output, but you can think about it's more like an auto-grading process. So now, how do we? Okay, case number 1. How do we assess the quality of your R1? Okay, I'll give you one example here, and then you should be able to see how to assess R2 accordingly. Okay, how do we assess R1? R1 is supposed to capture the errors where we change the input. So what we'll do is we're going to replace your implementation by a faulty one, which always remove the first element, for example. So that one should really fail R1. Okay? Replace by a faulty implementation that always remove the first item in the input. So that one there is guaranteed to fail your R1. So if you didn't really specify anything for R1, you just say it's true. Then of course, it's going to pass it, right? Or if you specify that incorrectly, right? So that's how we assess this one here. All right, guys, you want to do some quick exercise? How do I assess the quality of R2? Can you tell me the exact setup? Okay, so now we are trying to test for R2, right? Any suggestion? How should we set up the input and output accordingly? How should we do that? Anyone? I definitely should replace the algorithm by some faulty one. But how should the faulty implementation work?
Maybe get something that only checks the first thing in the input, and if it isn't your input val, then return false.
Sure, that's definitely going to work. So what Adrian said is you always search the search space is always just the first element, like a subarray of size 1. Or how about this? I just always return true. That's also going to work, right? That's another test case. Okay. All right, what I'm going to write now is also write down right now is also very important. Okay. So here I would say replace by, again, a faulty implementation, which, okay, I'm going to say do two things. Number one, the faulty implementation cannot modify the input. Why am I saying this?
You already tried that.
Because you
Already tried that before. It would fail the R1 again.
exactly. So guys, it's a very important insight, okay? You can see the way the assertions for postcondition are going to be checked. It's going to check for R1 first and then by R2 because they go in the sequential order. So if you want to trigger the failure for R2, you got to make sure R1 actually pass first. Otherwise, you will get stuck in R1 anyway first, right? That's very important. All right, A, it does not modify input. And B over here, let's say always return false. Yeah, here when I say return, I really means always set the output to be false. That's really what I meant, but you see my idea. All right, so I think this one also clarifies about how we're going to grade, but it was more important for you guys to really understand, right? So when you actually set up the implementation here, of course that's important, but how to write the contracts accordingly is also very important. All right, so especially to come up with the complete postcondition, we didn't give you too many hints about complete postcondition for lab number 2. We want to give you the opportunity to think about how far you can really think of the different scenarios where implementation might go wrong. We'll see maybe on Tuesday when I look at the solution. But before that, you really want to try it out, what you can come up with. Sophisticated one. Okay. All right, any question about this? All right, I think, before that, Daniel, go ahead.
Specifically about modifying the input.
Yeah.
You were just saying that like, as an example, right? Like, you didn't do
Sorry, are you talking about 1 or 2?
R1.
R1, yeah.
Because like since it's a constant value, you couldn't modify it anymore.
When I say you don't modify the input, it's as follows. Yes, sometimes, in this case, constant, but sometimes the input and output can also be specified as variables. Depends on our setup. So here, conceptually, you want to know that whenever you actually want to do the algorithm, input should remain untouched. Just conceptually. Yeah. Mm-hmm. All right, so I'll leave you to that. But I think that this is a very important part, just not just to do with the programming test 1, but also for your lab 2 and also in general, right? That's a nice component for the lecture that we want to learn from that. All right. Okay, why don't we take a very short break? I think we can take attendance. After the break, we can just do at least one exercise for the predicate logic. Okay, and then we are definitely Thursday, I will for sure move on to temporal logic. All right, so I'm going to leave that postcondition, precondition, algorithmic correctness discussion to you. Okay, and this is I got 3 exercises, and we're going to go over maybe at least the first one today, and then I got another 2. One of them is also about nested quantification, and we can finish the math review and get on to model checking, temporal logic. All right, so this one here, again, this is not nested quantification, so we got just a single for all over here. All right, so basically you're given some multiple choice over here. There might be multiple correct answers, or can be just one. Okay, so now we want you to choose the answer. One thing you can know right away. So there are basically 2 parts for each answer. You will say either it's a theorem or it is not a theorem. So you may just want to, first of all, decide whether or not it's true. If that's true, that means you can disregard these three, right? If it happens that this is actually false, then you can disregard these two, right? Etc. Is this a theorem or not? First of all, the universal quantification. No. Agree? Okay. Okay, I'm going to take that from you. Okay. Not a theorem. It's easy to see. Okay, not a theorem. So that means these two I don't really need to worry about because they're simply wrong. Because the first part here is already wrong. All right, so let's now go over these three one by one. Okay, at least some option here. Should this be chosen? When I say it's not a theorem witnessed by 5-0, that means I can use the 5-0 over here to show that this can be evaluated to false, right? Okay, let's give it a try just on this one here. I think that might be all we can do today, and we'll continue. So 5-0 here, just go plug in the number. So 5 natural number and 0 natural number implies 5 times 0 larger than 0. Right? So you can see this part here indeed is true. And this part over here is false. So you got true implies false, which would be false. So this one here is good. To show that the universal quantification is not a theorem, you got to give a witness that's going to show the violation. All right? Okay, I don't want to run over the time, but for you guys before Thursday, you can take a look at, before Wednesday. You can take a look at 4 and 5 to see how you can justify them. We'll go over them very quickly. And then if you look at notes template, I also got another one for you. And also the nested quantification, right? That's also something we're going to go over quickly on Wednesday. And then we'll move on to model checking afterwards. Thank you so much. I'll see you on Wednesday.